We're going to begin another lesson on electrochemistry this time. And electrochemistry is the area of chemistry concerned with the interconversion of chemical and electrical energy. In a galvanic, or also called a voltaic cell, a spontaneous chemical reaction generates an electric current. In an electrolytic cell, we have the opposite situation. We generate an electric current using some other means, and that's used to drive a non-spontaneous reaction. Right, here we have a strip of zinc metal, which is immersed in a copper 2 sulfate solution. The copper 2 produces the blue color. Electrons are spontaneously transferred from the zinc atoms to the copper ions, and in the process the neutral zinc atoms become zinc plus 2 ions and they go into solution. The copper 2 ions, which are in solution, then accept these 2 electrons and deposit out as copper atoms. And as time passes, we'll see a deposit of copper metal, and we'll also see a fading of the blue color of the solution since zinc ions are colorless. This is an example of an oxidation reduction or redox reaction. Now, not all chemical reactions involve redox. There is a mnemonic to help us remember this. This is oil rig, where it stands for oxidation is loss of electrons and reduction is gain. By loss of electrons, we mean the electrons are on the product side, and gaining electrons, we would have electrons on the reactant side. These two always go together. We can't have one without the other. And not every chemical reaction involves redox. Okay, so here we have zinc and copper used to construct a galvanic cell. On the left side, we have copper 2 sulfate, and in that is immersed a copper electrode. On the other side, we have a zinc electrode, which is immersed in a zinc sulfate solution. Okay, there's also sodium sulfate that's dissolved in here. The electrons in this galvanic cell will spontaneously flow in this counterclockwise direction. Okay, connecting the two compartments is what's called a salt bridge. Okay, without the salt bridge, this reaction would immediately shut down. Okay, that's because as copper atoms are converted to copper ions, we're going to have, when copper 2 ions are converted to copper 2 atoms, we're going to have too much negative charge. And so we need to allow the flow of ions, in this case sodium ions, into the copper compartment, and that will help keep the charges balanced. Okay, we have a similar situation happening over here on this side. As zinc atoms are converted to zinc ions, now you've got too much positive charge. And so we need to move sulfate ions in order to keep the charges balanced. Okay, so the wire allows transfer of electrons, but the salt bridge allows transfer of ions in order to maintain charge neutrality. Okay, here we have the galvanic cell connected to a voltmeter, and it's showing that the voltage is 1.110. 1.1. The two electrodes are called the anode and the cathode. The anode is the electrode where oxidation occurs. This is where electrons are produced. And it's called the anode because anions will migrate toward it, and we give it a negative sign. So oxidation occurs at the anode. The cathode is where reduction occurs. The electrode, this is the electrode where electrons are consumed. And cations will move toward the cathode. And we assign this a positive sign. Okay, so these are the two half reactions. And notice in the overall reaction, there's no electron turn, okay, because the two electrons and the two electrons will subtract out. This is shorthand notation for a galvanic cell. We start on the left side with the anode, and then we use a vertical line to indicate a phase boundary. Okay, so here we have zinc ions in solution, and a double vertical line indicates the salt bridge. Then we have copper 2 solution, another phase boundary, and then we have the copper cathode. Okay, if we have two species in the anode or the cathode that are in the same phase, we'll come across an example where we have iron 2 aqueous and iron 3 aqueous. In that case, since they're in the same phase, we won't separate them with a vertical line, but instead we'll separate them with a comma. Cell potential is measured using the unit of the volt, and volts measure what is known as electromotive force, or EMF, which is given the symbol capital E. And this is defined as the force or electric potential that pushes the negatively charged electrons away from the anode and pulls them toward the cathode. If we think of electrons flowing through a wire in the same way as water flowing through a pipe, voltage or EMF is a lot like the water pressure. Current, which electric current is what we measure the flow of electrons. That can be thought of like the flow rate of water through a pipe. The joule, the coulomb, and the volt are related by this equation. The joule is the unit of energy, coulomb is the unit of electrical charge, and the volt is the SI unit of electric potential. The coulomb is defined as the amount of charge transferred when a current of 1 ampere flows for 1 second. Accordingly, an ampere is defined as a rate of flow of 1 coulomb per second. Faraday's constant is a very useful quantity, and we'll be using this to 3 significant figures. It's 96,500. And what it represents is the electric charge on 1 mole of electrons. And so the units are coulombs per mole of electrons. Okay, well, we can relate free energy to cell potential using this equation. Okay, this is under non-standard conditions. This is under standard conditions. N is the number of moles of electrons that are transferred. In the previous example that we had with copper and zinc, that was 2. F is Faraday's constant, and E is the cell potential. Okay, so here we have the standard cell potential at 25 degrees Celsius is 1.10 volts for the following reaction. Okay, so let's calculate the standard free energy change. Okay, so we just substitute our quantities into this equation. Okay, we had 2 electrons being transferred. Note the minus sign here. Okay, so moles of electrons divides out, and then this is merely a unit conversion. A volt is a joule per coulomb, and this is converting joules to kilojoules. Because delta G values are typically very large numbers. So this is negative 212 kilojoules. Okay, next we'll introduce the idea of standard reduction potentials. All right, here we have a copper cathode and a hydrogen anode. Okay, so copper is getting reduced, and hydrogen gas is getting oxidized to hydrogen ions. Okay, this is what's called the standard hydrogen electrode. It consists of a piece of platinum foil that is in contact with bubbles of hydrogen gas at 1 atmosphere pressure, and with hydrogen ions in solution at a concentration of 1 molar. Okay, here are the 2 half reactions. Hydrogen's the anode, copper's the cathode. And the cell potential is equal to the sum of the oxidation potential plus the reduction potential. The measured potential for this cell is 0.34 volts. Right, so the standard hydrogen electrode has been chosen to be the reference electrode, and its half reaction values are by definition 0. Okay, that's just defined as 0. Okay, so this is the reduction and the oxidation. So both directions. Right, since the cell potential is equal to the sum of the oxidation plus the reduction potential, and we just said on the previous slide that the oxidation potential for the anode is 0. Okay, that means that the reduction potential in this case is equal to 0.34, which is the same as the overall cell potential. Right, here we've changed the other electrode. We've got a standard hydrogen electrode. Oops. At this time, the zinc is the anode, and hydrogen is the cathode. Okay, so that's just the opposite of what we had with hydrogen and copper. Right, for this cell, the voltage was measured at 0.76 under standard conditions. And since the reduction potential for the hydrogen electrode is 0, that tells us that the standard reduction potential for half reaction potential for zinc is negative 0.76. That is, okay, what we've done, we've solved this equation. Okay, so how did I get negative 0.76? Well, the oxidation potential, okay, would have to be 0.76 by difference. Okay, 0 plus 0.76 is 0.76. But when we reverse this equation like we've done here, we change the sign of E. Right, here is a chart of standard reduction potentials for various half reactions. And these are all compared to the standard hydrogen electrode. Right, so those half reactions that are listed above hydrogen are more easily represent species that are more easily reduced than the hydrogen ion. Those species that are below hydrogen are more difficult to reduce, more easily oxidized in the reverse reaction. Okay, so we could use the chart to calculate and predict what the standard reduction or what the standard cell potential would be for any combination, not just those involving the hydrogen electrode. Let's go back here. All right, so since zinc, okay, which is down here, this is listed as a reduction. It's negative 0.76. And copper is up here. Okay, so the one that is higher up, that will be the spontaneous reduction, and then the other one down below will have to be an oxidation. Okay, so we'll have to flip this reaction and change the sign for the spontaneous reaction. All right, so that's why it's negative, negative. Okay, so if we add these together, we get 1.10 volts. Right, here we have silver and copper. In this case, silver is the cathode rather than copper. Copper is the anode. So silver is listed higher than copper on the chart. Okay, so this is the value off the chart for silver. The reduction potential for copper is 0.34, but since this is an oxidation, we changed the sign. Okay, so we flipped the reactants and products here. Okay, and our overall reaction can't contain an electron term, so we've got to go through and multiply everything by 2, and that way the electron term drops out. And now our equation is balanced. Okay, this is an important statement here. Half-cell potentials are intensive properties. Okay, what that means is that the half-cell potentials do not depend on the amount of material. Okay, so while we went through, we multiply these terms by 2. We did not multiply the standard potential by 2. Okay, so other examples of intensive properties would be like temperature. That doesn't depend on the amount of material. Density. The opposite of that would be extensive, which do depend on the amount of material. Things like mass. Okay, so we add these together, and the overall cell potential is 0.46 volts. Right, in the next lesson, we're going to look at cell potentials under non-standard state conditions.